So now we go to multivariate models. This is again also, I think, a real core aspect of the book and one of the raison d'etre for us to write the book. Because we found that this field is really lacking a summary at the level of quantitative risk management. And many of the early developments, especially on the statistical estimation, I still remember a lot on the generalized inverse Gaussian, and so Alex and Rudiger really worked very hard on that. So by now it has become standard knowledge. So the basics of multivariate modeling, at this level of the course, we have seen all of that. So I go very quickly. There's nothing on the first 3-4 slides. It's just putting down a random vector, because we're now interested. Time is not there for the moment. It will be a while before we meet time again. We will meet time again when Rudiger starts with credit risk, I think.
Okay. We might reintroduce time at the end of the afternoon.
Multivariate time series. Multivariate time series. Yeah, sorry for that. So for the moment, it's not there. Sorry?
That is if you get through this.
Yes. Okay, so first of all, the joint distribution is a distribution of x1 and xd less than their respective given values. From the joint, you get the marginals. Marginal is h, so from a joint model, you get marginal distributions, nothing special. You can look at the marginal distributions of subblocks by just looking at the relevant part where you want to find the marginal distribution. If f is absolutely continuous, in particular, if f has a density, you can have a multivariate density. Many models are written, think of the multivariate Gaussian, at the level of the density. So you can work with densities. From the densities, you get the marginal distributions. This you all know. Of course, you know from a joint model, you get the densities. From the marginal densities, you don't get the joint model. And the standard example in any trivial course is you do discrete data. You look at a bivariate table of probabilities, you get the marginals. From the marginals, you can never fill out the full joint distribution in the interior of the discrete data, two-variate, for instance. It's trivial. We all know that. So, but I still say the joint model, that's the holy grail of risk management. If you have that, you can answer many, many, many questions. From the joint model, you get the marginal. You cannot go back. There are infinitely many joint models with the same margins, and that's where the copula starts to play a role later. Okay, so this is all well known. Very rarely, but I think in credit and within copulas, we may work with what's called the joint survival function. Now carefully I put the bar. Until now, the bar means 1 minus f. If I use the bar, this is a bold x, a big X, but if I use the bar for a joint vector, you see there's a big X. Then we use this function. So this is not 1 minus f of x, but it's just the joint survival function. And in medical statistics, the probability that patient 1 lives longer than 1 year up to patient D lives longer than 1 year, if they're all 1. Or if you think of default probabilities, the probability that the time to default is larger than x1 to xd for each of the D components. So I'm just saying that this function is typically very important in risk management. We will occasionally use it. Okay, well, I just mentioned that. It's not the same. If x is d-dimensional more than 2, then this course is different. Independence, we'll come back to that much more later. Two vectors are independent if the joint distribution of the two vectors is a product of the marginals. You know that, the product rule. If you have a density, then you can write down the product rule. Again, these are vectors, if you like. In d-dimensional, this can be k-dimensional, d minus k. If the joint density factors in the marginal density. It's always the product rule at the level of distribution, at the level of events, at the level of densities, whatever you've got at your disposal, it's the product rule. Okay? These components themselves of my vector are independent. We will typically say independent. Sometimes people want to stress mutually independent rather than pairwise independent. I mean, when we say independent, it really is globally independent, mutual independence, if the joint distribution is the product of the marginals. Okay? And again, you can write it down at the level of densities if you have it. So this is all standard we know so far. Again, fast. Well, we have used it. If I've got a vector, the expectation of a vector is the vector of the expectation. So I do expectations every component. So nothing special here. The covariance, we already seen it, is the mixed second moment. Now I start being a bit careful about the transpose. Our vectors are standard row vectors, and the transpose make them column vectors. I said it correctly. I signed it correctly, said it wrongly. Column vectors, and transpose make them row vectors. So always make sure that it fits here. There's the covariance. The ijth element of the covariance matrix is the variance, is the covariance between xi and xj. If I equals j, is the variance. Again, now I'm getting already a bit more careful. And you can say, oh, of course it's true. Well, of course it's true. It's one of the big sins out there that many people say, well, it's true that if the random variables are independent, then the covariance is 0. This you see here. Because if the variables are independent, then the expectation of the product is the product of the expectation. That's immediate from the dependence definition. And this is 0. And now the of course comes in the converse. Of course I know that. I've learned that in my first class on probability or statistics, that the converse is wrong. We all know that. And if you don't know, if you're not sure about that, then you better keep your eyes open for a couple of days more, especially copulas. Unfortunately, people often try to convince me explicitly and implicitly that, well, but perhaps it's almost true. No, it's not almost true. Often I see the statement, well, the covariance is small. Diversify. It's close to independent. It may be, but it may also not be. And believe me, in crises, it typically is not. So careful about this one. And this we'll learn, that's why the same color in copulas, right? Well, that's one of the main reasons for introducing the copulas, to understand what happens here. Now, correlations, once you have the covariance matrix, you can standardize by the standard deviations. That makes them live between plus and minus 1. That's a famous Cauchy-Schwarz inequality. Schwarz without a T. We know that the extremities are arrived at if your data is linearly dependent. So if you plus minus 1, even only have linear dependence, that's why it's called linear correlation, this will come back later. Keep it in mind, okay? There's a surprise there later. And now you have various properties. We already used these properties, so I will not lose time on that. That's just a standard probability calculus with variances, means, covariances. You should know. There's a bit of linear algebra. We will not do too much of that. But if you want to dig a bit deeper, you have to know that expectation is also linear at the level of matrices and at the level of vectors. And the matrix A always has to be such that AX makes sense. A is K times D, X is D times 1, so this makes sense. Standard calculus, so its expectation is linear. This is perhaps something more important that you should really, one of the formulas you should hang above your bed. That's one of the useful formulas. It's easy, but it's a useful one. The covariance of a linear combination, a vector, a matrix plus a vector, and the dimensions are so that it makes sense, so it's k-dimensional vector here. The covariance of ax plus b is a covariance x a prime. And again, you can work it out component-wise. It's immediate. There's nothing special about this, but this is one you should know by heart. So this is a sigma a accent, a sigma a transpose. If I call sigma standard notation, the covariance matrix of my vector x assumed to exist. Take k equals 1. Then make sure that the dimensions are correct. So it's a 1 times k times a k times 1, or 1 times d times a d times 1, so it's a number. So then you see that the covariance, let me see, the covariance of a primes x, and I'll take a very special one-dimensional a, so it's a vector. Well, one-dimensional, it's a vector now, sorry. Then the covariance of this is a prime sigma a. That's the same formula. Careful, the accent is now on the right-hand side. And this is the variance. This is a little thing you all know, again important, but this shows you already that covariance matrices are, by definition, positive semi-definite, because they satisfy this property. Okay, that's here. So it's all standard. If this is strictly positive, it's called it's positive definite. Again, it will not play a big role. Numerically, these things are important, but we will most of the time work with definite covariance matrices, and that only means that my data, I can invert the covariance matrix. Otherwise, I'm a bit careful with things like collinearity, and so I will not do that. The Cholesky decomposition, that's a power result. The Cholesky decomposition is a very powerful numerical result you may have seen in your high school days for solving Gauss equations or for solving numerical equations with matrices. It's a decomposition. It's somehow like taking the root. You have a semi-definite matrix sigma. Think of a covariance matrix. I mean, you make it positive definite, I don't care. Then you can always write this covariance matrix as a product of an upper and lower diagonal matrix. An upper diagonal matrix has only positive or non-zero elements, in this case positive, above the diagonal, 0 here, and of course the transpose vice versa. And of course, if you've got a diagonal matrix in a linear system, that's what you did as a school kid even, you can nicely solve your equations. So Cholesky is important. So we will use that. It's called the Cholesky decomposition. It's called the Cholesky factor. Okay? Lower triangle, upper triangular. One thing, if you really want to do the mathematics, but I will not do it, you should know about characteristic functions. Not for this course. But if you want to understand a little bit more of the main results and the proofs and all that in the book, you should know about Fourier transforms. It's a Fourier transform. You know that the distribution function of a vector or a random variable is uniquely determined by its Fourier transform. This is the Fourier transform. Now it is in d dimensions, so it's t1x1 plus t2x2 plus tdxd. That's a Fourier transform. Here's the famous I squared equals -1. This always exists, because the norm of this thing here is bounded by 1. So it always exists, the Fourier transform. That's nice about it. And as a tool, Fourier analysis is important. You will see it 2 or 3 times appearing. It will not be essential. So you may close your eyes if you see Fourier, well, at least Fourier transforms. Well, I think if I would open my eyes widely if I see Fourier, but never mind. Proposition 6.1, a symmetric matrix sigma is a covariance matrix if and only if it's positive semi-definite. And in the one direction to the right, that's exactly this statement here. So covariance matrix and positive semi-definite matrices in linear algebra are the same. That's why we can use so much of linear algebra. And this is unfortunate for some of you perhaps, is if you really want to understand multivariate models, you must brush up your linear algebra. There's nothing you can avoid there. It's linear algebra. You may even go to some of these more, no, not fancy theories, but important, like Frobenius theory, etc. It's so terribly important. If you go to factor analysis, if you go to high-dimensional data representation even, geometry plays a role, algebra plays a role. By the way, just an aside, and I can tell it here because one of the founders of Google was from, I think, EPFL, next door. One of them, I think Breen, I forgot now, one of the two was from, I think, from Lausanne. The Google search machine, the search machine is websites. One website, the other site, and links between websites. It's a huge matrix. And you can say, I normalize it by the number of visits from site A to site J. Most of these are 0. Why did Google, and I still remember it, I'm old enough, that the days of Alta Vista and all the other search machines, and suddenly Google came on the map. Now everybody is using Google. Even if I look at the telephone number of my colleague at ETH, I look at Google. It's ridiculous. I should have a telephone book on my desk. It uses Frobenius theory, which is a theory of positive matrices. It uses linear algebra. Extremely important. If you never read it, it's a bit of a strange statement now. Google in Frobenius. It's like self-reference. It's a bit dangerous. It's like dynamical systems. All right? It can be chaotic. All right. But I just want to pause and say, linear algebra, you cannot avoid it. Geometry, you cannot avoid in the multivariate world. We'll see a little bit of that, especially when Marius takes over later. Now, you can estimate the means and the covariance. Here are the estimators. You take the sample mean and the sample covariance and the sample correlation. You can write them down. A little side comment, I think we mentioned the book. It's not so trivial as it may sound. I mean, these estimators are not always perhaps the best estimator. Things like shrinkage and so, I will not go into detail, but there's a little proviso when using these. But for us, if we estimate the vectors of means, the covariance matrix, we use a sample estimation, the sample estimators here. But there's a little comment I could make there. We can make it unbiased, you know, the famous n-1, 1 degree of freedom if you like to subtract, but that's a standard for small n, it's important. So these you only know, nothing special here. Now I slow down. Now comes perhaps one of the most important slides of the course. I'm very biased, of course. This is the multivariate Gaussian. And really I should give a whole day a course on the multivariate Gaussian. In the old slides we had more slides of this. This is one definition. Now, if I give you 5 minutes, it's rhetorical, you won't do it. Write down your preferred definition, it's gone. I hope it's gone, yeah. Your preferred definition of the multivariate Gaussian. And I will collect all your papers. And it would be nice to see what definition you wrote down. I can think of 4 or 5 definitions. This is one of them. This is a constructive one. This is a simulation one. Because you see, I start with a z vector. You all know the z vector. Z1 to Zd, IID Gaussians. IID standard normal. And Marius told us yesterday, with current computer power, just inversion we can simulate from them. So the building block to start with is the independent standard Gaussians. We all know that. Where do I get the covariance in? Cholesky is around the corner. I give you a matrix A. You can think most of the time D equals K. Don't worry about that. We write it down, but you can take all D equals K. Just a bit more general in that case. A matrix A. Any matrix A. Well, essentially. You can calculate the mean. This is just a vector, so the mean is linear, so it's mu. Now the covariance. Remember? Look above your bit. There's this formula there. The covariance, well, if you shift, the covariance doesn't change. But here is A covariance Z A prime. Remember, that was the formula above your bit. This is A prime. I define it to be sigma. You see, this is little dots here. Because there was no sigma to start with. I define it to be sigma. That's always a positive semi-definite matrix. It's like the square. A prime. It's like taking a square. Or it is like taking a square. Later, going from sigma to the A, if I give you a sigma and you want to find the A, Cholesky. You see, that's and now you see, I've nothing done yet. I've just said I start with IID Gaussians, I pre-multiply by a matrix, I get a new vector, I add the mean, and I get an interesting distribution. I have no idea why I could call it multivariate Gaussian. I only showed you that the mean is mu, so this vector I can call the mean, and I only showed you that I can call the covariance is A prime, and I just denoted by sigma, nothing more. This is vacuous, doesn't have any meaning, it's just notation. I can do a bit more, but I can immediately skip it. I can calculate for this vector, and that's an easy calculation if you know a bit of characteristic functions, not much really. I can write down the characteristic function. Now this already starts to look a bit that we know. It's a bit looking like e to the minus a half t square in one dimension, but that's okay, it's there. Forget about it. Exercise. Transformation theorem in analysis. Show that if you do this construction, this is a random vector, that random vector has a density, and here it is. And now I look at your page, and that's exactly the definition we wrote down there, right? So that's a second definition. This is the Gaussian density. So now I'm saying, oh, well, but this we know. This is what we call a Gaussian, a multivariate, d-dimensional Gaussian distribution with mean vector mu, location, and variance-covariance matrix sigma. where sigma is A prime in this definition. So if you start with this definition, which is a trivial one to simulate from, because I can simulate this, Frank gives me his sigma, I do Cholesky decomposition, I find A and A prime, I pre-multiplied Marius's IID Gaussians, inverting, I have this vector, I know this from Cholesky, and I'm done. You just add the mean. You see the difference? And if I were now to ask you, how would you simulate from your model there? Well, you got an issue. You want to talk to Marius, perhaps. That's the difference in a constructive definition and an analytic definition. And this will come back later. This will come back later in a very nice little story related to a big investment bank in New York. Later. Now I know the density. I can plot it. So Marius will take the R code, and you have these plots of these distributions in well, 2 dimensions, I think. But you can plot all these things. Okay? Now comes the geometry. Now we go back to Euclid. How does this density look like? Well, it's rather complicated, but the dependence on x is only here. Now let's do in 2 dimensions. I draw the density, and the density may be anything. It won't be, but it could be anything, integrating to 1. And now I cut it. I look at the level set of the density. So I cut that complicated landscape, like across the lake here. That's France most of the time. I cut it, and I look from above. How do these level curves look like? So that means you put it equal to a constant. You put this equal to a constant, because these are all constant. So this equal to a constant. That's my level set. And now you go back to your school days. In Moscow, definitely your pre-university days. In Europe, less and less, I'm afraid. That's an ellipsoid. That's this equal to 5, for instance, and mu equal to 0. These are ellipsoids and circles. So you look at them. Depends on the sigma. If sigma's identity is a ball or an ellipse. So this is an elliptical distribution, we call it. Because the densities, if I look from above, it's like a Mexican hat that you cut pieces of. It's an ellipsoid. Interesting. All right, that's here. Also something you see, but now you have to think a bit beyond. One of the fundamental theorems and fundamental mistakes in finance. When are the components of the multivariate Gaussian independent? Now remember, if I have the density, the multivariate vector with the density is independent if and only if I can factorize the density in marginal densities. When can you do that? There's only one way you can do that, if this sigma is identical, the diagonal. As soon as you start mixing off diagonal, you start multiplying x1s with x7 and so on. No way you can factorize. So by just looking at this thing, you got one of the fundamental theorems of statistics. For the multivariate Gaussian, the vectors, the components are independent, let me call it, mutually independent, if and only if sigma is diagonal. If and only if all the correlations are 0. Now you see you can go back. Remember? Now I can go back. If I have, in this case, a bivariate Gaussian, bivariate with 0 correlation, then they're independent. So just calculating this number, the correlation, I can find independence. All right? My students, I exaggerate a little bit, but if they make a mistake in quoting this result, they really have a problem in getting a pass on my examination. Don't try to tell to me, when can you go back? And you say, oh, yeah, I can go. I'm not pointing to anybody. I'm pointing to him here. Say, when can you go back? Oh, yes, in the Gaussian world. That's not sufficient in my examination. That person should say, in the multivariate Gaussian world, which is very different from x1 up to xd or Gaussian. Koplas will tell you. So in the multivariate Gaussian world, independence and zero correlation are equivalent. Multivariate. So really, I could explain that 10 times. And I do it because so often people forget it once they're outside. Multivariate Gaussian is much more important to give you a multivariate model. The multivariate Gaussian, you saw it, it's on your paper. Or the components are Gaussian. Very different world. Big area of confusion in finance. Unfortunately, still today. And it's so easy. Okay. So we discovered that. How do you prove this? Transformation theorem. If you know your multivariate analysis, real analysis, you can prove it. So it's not difficult. Okay. Here, so this is the Mexican hat from above. You see the correlation gives you the slant of the diagonal here. So these are examples. So I'll come back to the T later. I've not discussed the T yet. How do you sample? I already did it. I have a problem. Sorry, I always take you there, but I have a sample. If I want to sample from your density, it's a problem. It's a big numerical problem. If I want to sample from my definition, which is equivalent, it's immediate. This is the sample I gave you, Cholinsky. All right? Now there are many nice results. I will just mention them. The proofs are fairly straightforward, transformation theorem, etc., 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 all characteristic functions. First of all, linear combinations of a Gaussian are Gaussian, multivariate Gaussian. If the vector is multivariate Gaussian, then the linear combination is Gaussian. I once had a very heated discussion, and this time I will not mention the name, the person, well, whatever, a very famous finance professor from the US. And I said, well, if x1 is normal and x2 is normal, I have no idea for x1 plus x2. He said, no, it's normal. I said, no. I said, no, it's the basis of finance. It's wrong. Well, you can see immediately if x1 is standard normal, z, and x2 is minus z, the sum is 0. So it's obvious. If x1, x2 is bivariate normal, then the sum is normal. That's this theorem, even in matrix form. Very important. So in special case, if I've got a multivariate Gaussian, and I multivariate, then every linear combination, every portfolio built on the Gaussian is again Gaussian. And of course, the parameters transform like means and covariance transform. For every B, a wonderful result, which unfortunately fell off the slides, the converse is true. If you give me a vector for which every linear combination is one-dimensional Gaussian, for every vector B, then the joint distribution is multivariate Gaussian. That lives under the name Cramér-Wald device. I will not say more about that. I call that, and I know these names I'm giving are a bit of a joke, but they have a pedagogical ground. I said, this is surely the fundamental theorem of portfolio analysis. Because it tells you if you want your portfolio to be Gaussian for all possible combinations, long and short, you want to be Gaussian, then you must start from a multivariate Gaussian model, and vice versa. So these are, for that bit of a joking way, I say, this is the fundamental theorem of portfolio analysis. In the multivariate Gaussian world, all portfolios are Gaussian. Very, very important result. We will be a bit more general later. The marginals, if you have multivariate Gaussian, the marginal are Gaussian. Quadratic forms is like if you take IID standard Gaussians, which is like a multivariate Gaussian with identical covariance, then the sum of the squares is chi-square. Well, if you take sum of squares of multivariate Gaussian components, you also find the chi-square. Okay, so the chi-square distribution, and this you can do for testing, QQ plotting and testing normality. So for testing, I'm just quickly mention these things. So marginal distributions, even at the vector level, these are vectors. At the subvector level, they're all Gaussian. Linear combinations, marginals, conditional distributions even. Testing, how would you test for multivariate normality? That's not so easy, and Alex already spoke about it. Think about the data, because if your data are, it's not written there, but it's presumed there, if your data are by definition highly skewed, perhaps you should transform them first. If it doesn't work, if there's a discrete component, well, surely you cannot have multivariate Gaussianity. Once everything is roughly right, you looked at the data, it's a bit symmetric, one-dimensional, it's okay, then you can look at multivariate cases. And you know that if we have, for multivariate normality, well, I already mentioned this result, there's various things you can do. Well, let me go here. You can do QQ plots for certain linear combinations. You see, well, okay. There are tests like Shapiro-Wilks. There is tests like Mardia's test. Is a directional. Mardia wrote a famous book on directional data in statistics. So now you're really in the world of multivariate statistics. There are the Yarke-Berra test, etc., etc. So there are many tests that Alex already mentioned. I will not go back to that. They're all related, let's say, to the chi-square distribution. Should be there somewhere. So there are various ways you can test the marginals, you can test some linear combinations, you can test bivariate, you can test the sum of squares. But none of these tests all put together are equivalent with multivariate normality. You know, I think I'm correct there, Alex. I mean, it's not so easy to get an equivalence test, I think, there. Okay, so but that's, if I can test up to several dimensions, several combinations, I'm pretty happy, also if I understand the data. Now comes the important example. Remember the BMW Siemens data. These were the data. Now you start thinking about as geometers. Don't look at the left picture. That's like saying, don't think of a pink elephant. Of course, everybody is looking at the left picture now. Look at the right picture. These are the data. These are the daily log returns of BMW and Siemens over the period Alex discussed. Here are the data. Geometrically, what do you see in this plot? What are the geometrical features? There are no wrong answers here. What do you see in this plot? Yeah? Ellipse. Yeah, ellipse. Where do you see the ellipse? In the middle. Okay, so in the center, there's this elliptical blob here. That looks pretty elliptical. Okay, what else do you see?
Correlation.
Well, you got very, very mathematical eyes, Frank. What Frank is saying, we see the sort of this increasing trend. It's correct. What else do you see? Ah, well, again, you got mathematical eyes. So where do you see tail dependence?
On the left.
Ah, left bottom corner. Ah, you see here there's a lot of action together. What else do you see? Now it's a secondary thing. Sorry? Heavy tails is here, yes? What do you see here? Nothing much. So there's nothing much having in the whatever, north, east, south, west, whatever corners. How do you compare this and that? It's skew. Now you all go home. And now you say, aha, I want to find a model that gives me a central elliptical blob, a bit of correlation thinking in there. In one corner shows me strong tail dependence, the other corner is much less. I don't want action in these corners. And you come back tomorrow with me with a nice parsimonious model exhibiting that. Parsimonious means with little parameters. We're not there yet. I would not do it. Not there yet. Forget about copulas. Okay? That's the job I have. Now you can say perhaps the Gaussian model does it. No, the Gaussian model does it not. That's left-hand side. Now you can open your left eye and look at this picture. This is the best fitting Gaussian, bivariate Gaussian model. Maximum likelihood fit we did on this. You take your data, fit the best, you estimate mu and sigma. That's the best fitting. We do get the elliptical part. We don't get the extremes. Remember, the extreme are 15%. If you're a risk manager and you look at your Gaussian model and you want to stress test, for you, these crises would never exist. And now I get again the story, well, once in a lifetime of the universe. It doesn't capture it. So the Gaussian is out. No way. This is the best Gaussian fit. You cannot improve it. That's the best fit. It does not, from a risk manager's point of view, capture the essential. Now comes the exercise, so I will give you the solution, so you can go out tonight to Ushi and enjoy yourself. I will now make a bridge from this model to that model in, not Clayton copulas, in a parsimonious way. I want to give you some very basic intuitive model building to go from left to right. Parsimony, this is the famous statement by George Box about building models, and models are wrong, all models are wrong, some are right. Look at it more carefully at this quote. He says something about parsimony. We should build models with as few parameters as possible that really describe the main aspects. He has this statement about if you give me 3 parameters, I can model an elephant. If you give me 5 parameters, I can wiggle his trunk. That's the famous statement by George Box. Well, now I can do the testing. The left plot, Gaussian. The right plot, clearly non-Gaussian. The real data, the inverted S. The second margin, highly non-Gaussian. We know that. The simulated data, very Gaussian. Of course, it is Gaussian because it's simulated from a Gaussian model. We have done good simulations. He was saying earlier, let's see whether the theorems are correct. You know, I nearly jumped up and said, well, we've proved they are correct. Of course, he really meant, no, I know. yeah. So it's always good to let the simulation see, did the mathematician do a good job? Here is the vice versa. So you see, now we look at the sum of squares. There should be chi-square. Do we do chi-squared degree of QQ plot? The real Gaussian data, they're fine. Oh, I switch it off. The real Gaussian data are fine. The others are way off Gaussianity. So no way, and that's enough. I don't have to do beyond that. I don't have to do more formal testing. I'm convinced it's non-Gaussian. I'm going to build a bridge from the Gaussian world, my best Gaussian fit, to reality. I want to keep as much as possible my old model because people think in terms of Gaussianity. So I want to keep the advantage of the Gaussian. I want the easy inference. I want to be, the driving parameter should be still the mean in the covariance or some matrix sigma. It's like keeping the volatility. If I can, perhaps I can't. In extreme value theory, I couldn't. Here I can. So let's try to keep that. I want to have linear combinations. Portfolios should have easy distributions. The Gaussian has it. This is famous theorem. Linear combination. I should have marginal distributions, I know. It's normal here. I should have conditional distributions, I know. It's normal here. Quadratic forms are known. Convolutions are normal. Sampling is straightforward. By definition, it's straightforward. And independence and uncorrelatedness are equivalent. Wouldn't it be nice if I or you can give me a model for the real data that has as much as possible of the previous advantages? That would be cool. That's model building. Rather than starting to build the model, in German you say the grüne Wiese. You just start building without thinking. Think about what you want to keep in your model and then see how you can achieve it. So let's do it. Okay? Well, the drawbacks, I don't have to repeat them. The drawbacks of the Gaussian are mainly the whole dependence is described by the covariance matrix. That's still perhaps okay in this case. But the drawback is definitely the tail heaviness. It's just not heavy enough in the tail. It's very symmetric. And we already saw symmetry is also. So it's tail heaviness, symmetry, etc., etc. This is the second most important. I'm nearly there with a little story of the big investment bank in New York. This is my definition. I said, well, I go back to, remember, if there's no W here, I have my Gaussian model. Remember? And that's how I define Gaussianity. That's not your definition, but mine, or his. And now I just do a slight change. I pre-multiply this construction here by a random variable, scalar, one-dimensional. Independent, whereas the other randomness here. I only do that. The square root is there because later I will take squares, and then it's just W. Not important, the square root. This is just a positive random variable. Later we will use the so-called inverse gamma, or inverse chi square. A standard will come with some one-dimensional random variable. So you can have your model, you can have your model, you can have your model. You just change the W. Okay? You can do whatever you like. But W is independent of Z. The main point being is I'm not walking away. Remember this bridge, the normal data reality. I only add on the normal model this slight change here. Very slight change. That opens a fantastic universe. Now, what is the intuition behind this? This is like you add a random shock to your covariances. If you can still interpret it as your covariances, AA prime, the W is a number, it's a random number. It goes as a square in your covariance matrix, but you shock all your elements by the same number. It's like you build a model now where you randomly shock all the elements of your covariance matrix. Clearly you get dependence, because now you suddenly have this common shock for all the covariances. I hope you see this. If not, I can just do the calculus, right? So this is a positive random variable. The special case, if I've got a degenerate, if it's just a constant, I give the old model back. And so you can interpret as a shock affecting the variances. You see the W shifts. If I take the conditional distribution, just what I said, the W shifts here if it goes with a square into the covariance matrix. So it's just a random, for every time you sample your omega, you have a new shock in your system. But of course, the shock is determined by the distribution of W. Now, I will not spend too much time on the calculus. I could, and do all the calculations. Let's just summarize them, because I think I really want to go to the more applied stuff. We have till 12, isn't it? Yeah. So now the problem is, for those who know stopping times, there's no stopping time here. I should have a stopping time here, I think. I don't know when I have to stop. We'll see. Just cry out. Okay, now you can do many calculations. You can work out the expectation. Is the expectation of, if we start here, and if you define y to be the original variable, the Gaussian, you start with multivariate Gaussian. You can calculate the mean. You can calculate the covariance. You need finite mean of the W. And you can do the calculation. Here comes one little detail. The covariance of your new model, X, is not the covariance of your old sigma, your old Z. Remember, AA prime was the covariance of that component, your sigma. Clearly, this W enters, or the mean of the W, or the variance. And so you see it here. So you get the mean. That's why we took a square root. So be careful. We had this yesterday when Alex said the nu over nu minus 2. Careful in these models, if you go from one to the other, there's a slight correction on the, but the correlation, this factor, of course, but the correlation drops out. So the correlation is not the same. This is already good. It's not bad. Because I like to think in, well, some people like to think in terms of correlation. Well, the two models have the same correlations. The AZ, which is your multivariate Gaussian you start with, and the new one. I haven't given a name yet. It will come immediately. The characteristic function you can work out. Now, here I'm a bit hesitant to go too deeply, because this is later important. If you calculate the characteristic function, you see some structure comes out. And now, of course, this W enters. This is a number, 12, for instance. This people call the Laplace transform. So the Laplace transform, which engineers also know very well, positive signals, the Laplace transform of W in this point here becomes important. That helps us to give a notation for this class, because I've not given a notation, and I do it here. This new vector now gets a name from me. The new vector is a multivariate mixture, that's an M, mixture of Gaussians, because I mix Gaussians, okay? That's the W construction here that's called mixing, okay? I mix them. Input parameter mu, input function sigma. Sigma is not the covariance of X. Sigma is the covariance of the input multivariate Gaussian, okay? Slight difference. And the W plays a role. I could have written here W, or the distribution of W. but it's slightly mathematical better if you think in terms of the notation-wise, in terms of the Laplace transform. But forget about it. That is not an issue. It'll be slightly an issue later if we go to, whatever later, to elliptical distributions, because then the notation becomes a bit more involved. But okay, for the moment now. Now comes a little exercise. It's very easy. It's immediate. Let's now, geometry. Let's look at the density. Now I look again of your paper. What have you worked out as density of this? Well, here it is. What's the density of this vector? Well, it's the definition. The density of a random vector of this, in this thing here is a conditional density given W is little w, and you integrate out the distribution function of W. That's just a standard way of working with conditional densities. This may have a density, then I write a density here, or to be pedantic, this is Stieltjes, but never mind. So this is just a definition of conditional density. Okay? Now, I know by definition, if I condition my W to be little w, then it's Gaussian. Okay, because this was immediately from the definition. Okay, if I take my vector, I condition it to be 15. I look at it, what happens? It's again, it's multivariate Gaussian. So it's a multivariate Gaussian. I can write it down.
Yeah, but shouldn't the lower limit of the, shouldn't you integrate from minus infinity?
No. W is a positive random variable. I take a square root. No, W is always positive. Okay. So I integrate for W. Okay? So, but this is immediate. Now, this density I know is the Gaussian. So what's the geometry of this distribution? Now I look again at the Mexican hat from above. I cut it. Sorry? Elliptical. It's much more complicated, but there is only one point where the x dependence plays here. If I put this integral equal to a constant, this must be a constant here in x. That's the only place I can have the x. That's an ellipsoid. It's an elliptical distribution. Oh, that's great, because you wanted to have these elliptical blobs there. So I got it. Oh, you don't know that yet. Wait, Frank, wait. He says you don't have the extremes. I don't know. Well, I do know. Well, we'll check. All right? What is my freedom I can work with is a W. For any W, I've got this. Let's now get some W's. Well, first of all, these things, there's a lot of properties of linear combination, marginals. I just leave them. This is an important one. All linear combinations, again, belong to the same class. The parameters change. This is good, because this you need for portfolios. So that's a very good result. So linear combinations stay within the class. The parameters change. So that's very good. Simulating, why should I bother? You know how to do it. Because this is an explicit definition. I'm nearly with my story there. I'll come back to you. Because, this is a definition. How do I simulate? I first simulate D independent standard Gaussians. If you want a given sigma, I took the Zariski decomposition to find the A prime. I multiply my DIID Gaussians with A. Now you come to me with your W. Let's say you take W is a chi-squared D. Oh, this is easy. I simulate a new set of DIID random variables, Gaussian. I add them up, square them, that's chi-squared D. So life can be easy or difficult depending on the simulation of W. But it's a one-dimensional random variable. So you give me your favorite model, and I simulate for you. Oh, I'm there. It's done. It's trivial. Even if I'm not a computer buff, I can program that, I think. But don't test me. All right? It's straightforward. Why is it straightforward? Because I did very careful construction of parsimonious model building. Okay? And now I'm almost there with the story. Now I can take many examples. If the W equals 1, it's a multivariate Gaussian, nothing new. Now you can look at models where you have kind of stress mixture models. I can take W as a two-point distribution. Remember, the W stresses the covariance. High covariance, high volatility, if you like, in some general sense. low. You can take a 2-point distribution, a 5-point distribution. You can take a very strange combination of different aspects of Gaussian worlds mixed together. You can do that. I will not discuss the hyperbolics. They are used quite a lot, especially in high-frequency data. I'll look at this. Now I will take a very special example, and this is an exercise you can do. Often if you do exercises, it helps you to slow down in your mind and think about what you're doing. Finding the result is always nice, but by thinking, let's say 15, 20 minutes, half an hour, depends on your calculus, you're thinking what you're calculating. Let's take W is 1 over V, where V is a gamma distribution. It's called an inverse gamma. It's also chi-square, inverse chi-square. An inverse gamma is absolutely standard distribution with degrees of freedom or a number nu given. Okay? The mean exists if you calculate this nu over nu minus 2. If nu is greater than 2, then there are finite variances. So then the covariance you can calculate it. So, but this is just an example. Right? This is trivial to simulate from. Because you have to simulate from a gamma. And if nu is an integer, an even integer, it's just a chi-squared type of simulation. So back of an envelope. And so you can simulate easily from this thing here. Now do the calculation. You really have to, if you do it once, it's nice. Or you ask you have children at school age, ask your son or daughter to do it. They just have to know how to integrate. Plug in here for the W, the density of the gamma, and do the calculation. If your son or daughter or nephew or niece has done it correctly, they will come up with this here. Is the gamma the function is coming up. This is called the multivariate T. We already saw that yesterday. All right? That's a multivariate T. Now comes the story. This must have been mid-90s. A famous investment bank in New York called me and said, oh, well, we're starting to look at non-Gaussian models, and we use now for our data modeling, we use the multivariate T. And like in York, no, sorry, they written down the density. I said, how would you simulate from this? And I should have said, well, let me think about it. It's an interesting question. But I was rather naive, and I immediately said, well, it's trivial. This is the way you simulate it. So this here. And I told them, which is of course, you should never do that. If a big bank phones you, say, well, let me think about it. I'll come back to you in a week's time. No, I'm just joking. But it just shows you simulating directly, even with good numerics, from this distribution is non-trivial. Inverse, well, ask Marius. But if you know that this interesting distribution, this is one of the workhorses of finance nowadays, the T. Some people say the whole world is about T. There's even books about that. Eckhart Platon, the world model of finance. Then you must simulate from this. But if you know that this density, this random vector has this representation here, it's trivial. You can just simulate it. That's what I call parsimonious thinking. That's what I hope you learned in this particular thing. Now comes, and I pressed Marius to do that. It gave him perhaps a couple of hours work one evening. I said, now I want to go back to my data. These were the finance data. BMWW. I remember? Elliptical blob, extremes, a bit asymmetric, sorry for that. The best normal fit, nothing getting there. The right-hand side is the best multivariate Gaussian fit on 3 degrees of freedom. We gave it 3, I don't think we estimated. You can estimate a 3, it will be very close to the 3. But it's, let's say, the best fitting T model. This is not bad. What's good about it, I can ask you, but you'll see it. What's good about it, I get, of course, I'm not predicting these events, but I get the right range. Look, minus 10, minus 15. My model captures 15% drops in these share prices between these two German stocks. It also gives me, and Frank is already jumping up and down, it gives me a bit of symmetric in the right tail. It's clear, it's symmetric, it's a symmetric model, it's elliptical. It has ellipsoidal center, but not center. It's an elliptical distribution. And it satisfies all the nice properties I have. Now you can say, and Frank can say to me, well, this is not good enough. I want to get rid of these points here. I want to get skewness in this tail here, extreme events here, but not there. But at least, I really hope, and if not, then I have failed my duty. I really hope that you understand how you should think about model building beyond well-known standard models. You start with your standard model, you think about possible changes, you do changes which you economically understand, the mixture modeling, you stress test your covariance entries by this independent random variable, you find models that have beautiful properties. I'm not fully there yet, but believe me, I think I forgot now, there's a paper by Philippe Jorion on the 1987, I think, or LTCM crisis, LTCM in 98, where also it was said what happened to LTCM, the hedge fund. The drop down was a once in so many years experience. If you do just the multivariate T models, I think it became, with reasonable parameters like these, I think it became 1 in 70 years. So you already get qualitatively estimates in the right ball game. If you now say, well, but this asymmetry, which I see in the data, I really have to capture, then you go to the next one, does this sort of. Now it's okay. Let's now add an extra component. Now also randomize the mean. You see, this is very different from copula modeling. And that's why copulas come later. But copulas are fine, and I will tell you how fine they are later. But this is different. I don't think of copulas. I think of economic ways, random mean, random shock in my covariance. That I understand economically. There is a copula behind this. There's a T copula. The joke comes later in the course about the T copula. But that's the next stage. Believe me, if we now do it with a good choice of the mean, and again, simulation is easy, I get the skew models. You can have as skew as you like. So that's the way we do it. We will not treat that. We can do the calculations. We won't do that. I think I'm supposed to stop here, and somebody is taking over now. Marius, I think it's enough time, isn't it?
Yes.
Marius will now talk about another way, a more geometric way of looking at the elliptical. So from my introduction, you learned that elliptical distributions, which I didn't call like that. I said they're elliptical, but I called them variance, covariance, or variance or covariance mixtures of Gaussians. That's what I did. Okay? Now Marius will give a slightly different view on that, which is highly relevant for portfolio analysis.
Okay, so we've learned about the multivariate normal model and extensions as the multivariate T with a factor of square root of W with a stochastic representation, essentially, right? This is what Paul stressed. You have to look at stochastic representations to extend your model. Then sampling is easy and so on. And a different way of getting to a even more general class of models than the normal variance mixtures you had with the square root of W is to get to elliptical distributions. Why do we want to study this even more general class? Because in chapter 8, I believe we will have a result that for all random vectors x following a multivariate elliptical distribution, value at risk is subadditive. Yeah, so that builds a link between chapter 6 and chapter 2, essentially. And so that's why we are interested in this even more general class of distributions. Now, the way this class is constructed is slightly differently than going from the multivariate normal to the multivariate T. And it's easier, let's say, and also essentially the classical way to introduce elliptical distributions, to first study a subclass of elliptical distributions. And that subclass are spherical distributions. And the names will become clear soon. So what is a spherical distributed? And again, we look at random vectors. We don't look at densities here. So a spherically distributed random vector, y, is a random vector that is in distribution equal to a rotated or reflected version of itself. So it's essentially invariant distributionally under rotations and reflections. Now, you can go home, you didn't learn anything. How do you how do you think of such a random vector y? What is it? How would I simulate it? So that's not given in this definition, unfortunately. But you can already think about the geometry in the sense that, it must be like, how would the points look like if I sample it? They have to be invariant if I rotate them and, or even reflect them. So maybe something like a circle would do, right? Yeah, that's where the name comes from, the sphere, essentially, then in higher dimensions. But 2 dimensions, the circle. Now, there's a very important theorem, and of course it's proven in the book, about a characterization of spherical distributed random vectors or spherical distributions. And it says the following are equivalent. So first, my vector y is following a spherical distribution if and only if there is a function called the characteristic generator with which I can write the characteristic function like that. And essentially, you see the characteristic function, a bit of the same considerations as before with the density. The characteristic function is constant on spheres, on circles. Now, the characteristic function didn't play a too big role so far, and it won't. We rather look at stochastic representations at the random vectors. But if you want to prove the properties we will later quickly discuss about elliptical distributions, then there's no way around around characteristic functions typically. They also typically give you the shortest proofs for properties and results. So this is what we will not encounter too much anymore. But the third part, so essentially reading y is spherical if and only if this result holds, this is very important. Because this tells me, y is spherical if and only if every linear combination is in distribution equal to some constant, being the length of the vector, times one of the components of y. And the only thing to take away here at the moment is the mathematical or probabilistic beauty of this result. Namely, that I can rewrite something that involves a multivariate random vector, something high dimensional, in distribution by something that's univariate, by a single random variable. And that's extremely helpful. That's for many purposes, also especially in Chapter 8, then, where we learn that for all elliptical distributions, value at risk is subadditive. And the proof is actually, it's not too complicated, and the proof is exactly based on that result. So it's an extremely beautiful probabilistic result, essentially playing back the multivariate case to something univariate in distribution. So very, very helpful result. But still, all linear combinations being in distribution equal to one of them, still, it's kind of a recursive definition, if you like. I still don't know how to sample from that. I still don't know how to think about spherical distributions. I would like to have something like Paul represented, a stochastic representation. So this is very important 2 words, stochastic representation. I want a representation in distribution of my more complicated high-dimensional random vector in terms of simpler components, components I can simulate, independent normals and transformations with the Koleski and so on. So simpler components. And here is the result. So it says that a random vector y is spherically distributed if and only if it's in distribution equal to r times s, where r is a positive random variable, similar to the square root of w before, and s is a random vector, so similar to your set before, but this is now distributed uniformly on the unit sphere. And there are ways to generate points uniformly on the unit sphere. That's not very complicated. You can use your set vector from before. You will see that in a minute. But this is a very nice way of thinking about spherical distribution. So I essentially take points uniformly on the sphere, and then for each of them, I build a line between the origin and that point, and I scale that out randomly by realizations of R, of that distribution of R. And yeah, so that spherical distribution in the bivariate case is, of course, a circle. How could you immediately generate points uniformly on the circle? Just take a random angle between 0 and 2 pi and take the corresponding point where you are. So that would be an easy way to generate points uniformly on the unit circle in the bivariate case. And then you take, let's say, an exponential distribution, and you simulate as many points as you have on the circle, and then you scale them out, and you will have a spherically distributed.
Is it easy to do on more dimensions?
Yes, of course, it's easy. There's an easier way to sample from the sphere in higher dimensions, and we will do that now in a second. Yes, you have to. It is a very good question to show that the method works. I would take characteristic functions, which we don't do. But yeah, you will see that it works. I will show you these plots in R. Now, here you see I started exactly with, well, I can only plot in the bivariate case, so I started with points uniformly on the unit circle. And then I took as the radial part F distributed random variables. I multiply with D, I take the square root, and so I scale each point out or further in depending on my realizations of R. Now, why did I take such a complicated distribution function here? Because that's exactly the distribution function of the radial part that gives me a sample of a special case of the multivariate T distribution. Now, these spherical distributions, they can reproduce special cases of the multivariate T distribution you've seen before, and that's such a case. The spherical distributions are no generalization yet of what Paul did. It's not so easy to build a link between the two. But we will look at the generalized version of the spherical distributions, the elliptical distributions, and they will be a generalization of the normal variance mixtures Paul talked about. Yes?
One of the students was a bit confused in the beginning without mathematical background on the little omega which is there. So it's very important, this picture, that we sort of resample. Mario said it. So we sample these 500 points, but every sample is an omega.
Yes,
So
yes.
you sample the first point, then I sample the R, and I multiply them. So the first point may be pulled towards the center. Then you sample the second point on your circle, and you sample your second R.
Independently of each other. That's important, independent.
It was, and it's not important. But that's where a bit of the omega thinking may come in. So it's important that you see. It's not that you sample everything and then an R, and then how do you give this? So point by point you do this.
Of course, if you take the very same R, what you would get is simply one bigger circle or one smaller circle, right? I do these exercises with you in R soon, so.
And D here is just a multiplier D.
Here, you mean, the D? Yeah, that's just a multiplication. This is a bit of abuse of notation here, of course. This is a distribution, so I sample from that, and then that sample I multiply with D and I take the square root. It's all in R, it's all there. Give me a second, we are there. Now, in R, I actually, well, we come back to these pictures. I slightly take a different direction. So you see one set of constructing a sample from a multivariate elliptical distributions on the slides, and then one version you have in R. Because I can first multiply with the radial part, and then do later on the Cholesky decomposition. I can do it the other way around. So there are two versions. Yeah? Good. So we go from the circle to these spherical shapes. But of course, the point is, when do you see such a data? Yeah? Paul showed you the BMW Siemens data before. You never see circles as level curves in your data. Yeah? So this is just for us a building block for doing the next step, going to a more flexible model. And that more flexible model are the elliptical distribution, multivariate elliptical distributions. Now, if you know the spherical distributions and if you study characteristic functions to derive a lot of nice properties about spherical distributions, things like the covariance of the uniform distribution on the unit sphere and all of these things, then you can all use them as a building block to understand elliptical distributions and properties of elliptical distributions. Because to go from the spherical to the elliptical world, how do I go from the circle to the ellipse? Well, I do exactly that affine linear transformation. Yeah? So that's a very simple step then. All I do is I take an A, which is the Cholesky factor of some covariance matrix. I also want to stress that some covariance matrix, not necessarily the one of X, yeah? Because the radial part plays a role as well. Yeah, so I take this Cholesky factor, I multiply it with my spherical random vector, and then of course there can be a mu where I shift my whole random vector, a location parameter where I can shift my whole random vector somewhere else. Yeah, and the language is very important here. I always stress when I teach that, I always stress the difference between a mean vector and a covariance matrix versus a location and a scale. We speak here in terms of a location, and the sigma would then be a scale matrix, yeah? But those are not necessarily the mean of X and the covariance of X. Now, if the mean of X exists, then it's indeed equal, but it doesn't have to exist. Yeah? It depends on the radial part. And if the correlation matrix of X exists, then it's equal to the correlation matrix corresponding to that covariance matrix. But the covariance matrix of X itself, again, if it exists, depends on the sigma plus, well, not plus, but multiplied with a factor, and that factor essentially contains the information that, of the radial part as well. Yeah? So the radial part has to come in at some point. And you saw the same before when Paul talked about the square root of W and the covariance matrix of the normal variance mixtures. There you have the square root of W in the covariance matrix as well. You saw it for the multivariate T. There you have the nu divided by nu minus 2. Yeah? That's essentially that factor you also see here. Yeah? So very careful with mean and covariance here. Good. Now I should prove to you that what we do now is indeed a generalization of what Paul did earlier with the normal variance mixtures. And so first of all, I can take my stochastic representation of Y being R times S in here and get a nice stochastic representation of an elliptical random vector. This is extremely nice for us, right? So X is just mu plus R times A times S. So this is my stochastic representation. And to show that the normal variance mixtures are a special case of the ellipticals, all I have to do is I take the stochastic representation Paul gives me and I try to rewrite it such that I get it in this form. Because then I'm done. Then I know this class of distributions is a subclass of the ellipticals. And the way to do it is, here you have your normal variance mixture stochastic representation. You just pull out the norm of Z, and then this will be your new positive random variable, so that's your radial part. And Z divided by the norm of Z can be shown, first of all, to be uniformly distributed on the unit sphere. Yes, that answers your question, Frank. This is exactly how you would generate from a uniform distribution on the unit sphere. And one, surprisingly, but I don't want to go in detail here, one can also show that R and S are independent, so this is really exactly the stochastic representation of an elliptical. So all normal variance mixtures are indeed special cases of elliptical distributions. Yeah? Very beautiful results here. And so now let me go back for a second to that slide. So we did the first step. We started with S. We went to the spherical distributions multiplied with the radial part such that we, in the end, hopefully get a T. This is already a special case of the T. And then I do the location scale transform. So my scale is now the Cholesky factor. So you see how it turns from a spherical shape into an ellipsoid, yeah, the sample cloud. And then I move that to the upper right corner with a mu, with the location parameter. Yeah, so, and this looks now much closer to, well, this is actually a multivariate T sample now. Yeah? Just constructed through the idea of sphericals. Good, and then there are a lot of properties which you can derive by elliptical distributions. The bottom line is that most, but not all, properties of the multivariate normal do carry over to ellipticals. Yeah? So, for example, I mean, you've seen special cases. Obviously, now you see the normal variance mixtures are special cases. So you've seen these properties before. So the density can be written in this form. And again, you see that the level sets of the density are ellipses, essentially. Yeah? And hence the name elliptical. So this is also what we see in the data. And then linear combinations can be shown to be, again, elliptical. here's your famous result that now is the most general result for having known distributions of linear combinations of random variables. So if I have a random vector which is multivariate linear, then all linear combinations are univariate elliptical. So this is now the same, obviously, as for the normal variance mixtures. This is especially the same as for the multivariate normal distribution. And if you go back to chapter 2, Rüdiger yesterday very quickly looked at it. This is underlying the variance-covariance method for approximating or computing your loss distribution function. Yeah, so there we had two assumptions. X was multivariate normal, and we approximated our loss operator by the linearized loss. So I have a linear combination of the x's in there. And then my hope is that I know what the distribution is, the loss distribution, and from there I can calculate value at risk and expected shortfall explicitly. And that you can do even for this more general class of elliptical distributions. So now you know the variance-covariance method will still give you explicit risk measure estimates even for other distributions than the normal. And this is about the largest class you can easily get. Yeah? Good. Then the marginal distributions are again elliptical. Quadratic forms are in distribution equal to the radial part squared. And that can be, for example, used for goodness of fit testing. So I can recover this from data, essentially, and then test it against my theoretically assumed distribution underlying. Yeah? So I could use a QQ plot, for example, something univariate again, which can be very helpful in checking whether I actually have data from a multivariate T. If you give me data from a multivariate T, this is one way I can do a very simple univariate QQ plot goodness of fit test. Yeah? Of course, I can also test that formally with many of the tests we had in chapter 3, essentially. Good, but this is...
Page 149, just very briefly.
Yes, here it is.
So this is an example of the T distribution, the multivariate T. Take sigma diagonal. So then we have zero correlation, because correlation is invariant on the... This is a standard example, I would say, outside of the world of copulas, of a random vector where zero correlation does not imply independence. Because if your sigma is diagonal, you have the sum of squares and the 1 plus. You cannot factor that in products. For the T distribution, zero correlation for the T does not imply independence. The example. If nu goes to infinity, you get a Gaussian, you get an E, and then suddenly by magic it works. So that's okay, sorry.
Good. So again, it's quite a bit of theory here. I would like to challenge you a little bit, also challenge a little bit what Paul said earlier concerning sampling. You saw on the slides one random vector, but in practice, you want to have n realizations, right? And this is actually not so easy. It's actually, even for the multivariate T, so critical, partly numerical issues, partly the way R works on matrices and so on, that I wrote a paper about this. So it was even worth a paper. In the R journal, there's a paper on sampling from the multivariate T distribution. Very nice with the stochastic representation. Of course, same notation as here. Read it. It's a very nice one. But I go very quickly through with you with, in R, of course, with building these multivariate distributions. Good, so there's the script. It's called Constructing and Sampling Multivariate Distributions. There's a little bit of playground concerning building correlation matrices. So you start with the Cholesky factor, and you go to the correlation matrix and going back. So you can execute that. There's also a function of getting the correlation matrix from a covariance matrix. I do that manually. I do that with a function in R, and so on. So this is not so important for us. I look at other decompositions as well here. But here the magic starts. So here we start with the multivariate normal. So I want to have 1,000 samples. In the bivariate case, I can easily plot that then. But the code is written so that you can easily use a different dimension here as well. And I sample that set. And here you already see the difference to what's on the slides. It's not just these sets. It's an n by d matrix, essentially. And of course, if you sample IID, it doesn't matter how that matrix is filled. But be aware, it's very important to realize that in R, matrices are filled column-wise. Yeah? So, and actually, it can happen that instead of sampling normal variance mixture, you accidentally sample a mean variance mixture, which also mixes the mean, which is not even elliptical anymore. Yeah? So be extremely careful here. Test the samples you get. So this is essentially 1,000 independent normals. And then I want to put some covariance matrix on top. Yeah, so I get this shape. So I go through fairly quickly, but just highlight the most important aspects. Then, of course, I can move that somewhere else, right? So this is just my mu, essentially. Now I can even make the correlation smaller, yeah, and overlay that sample. So you see, of course, the smaller my correlation, or the larger in absolute value, actually, that's the right way of saying it, the more my samples lie on a line, right? This is what Paul mentioned. Correlation being plus or minus 1, almost surely they lie on a line. So this is what we had too. So this seems to work as well. I can switch the sign of the correlation matrix. Yeah, so I simply get the slope in the other direction. And I would like to start from this very same sample and now go to the multivariate t by bringing in that square root of w factor. So I sampled 1 over a gamma. By the way, this is how these samples look like in log scale. And then I multiply here the square root of w to a times z. But you see what's here in the computer. I need to transpose my set, then matrix, careful, matrix multiply with a, transpose that again, multiply with square root of w, and then repeat the location vector correspondingly. Yeah? So, and here this is a vector, this is a matrix. But our matches recycles the values correspondingly. I just have to make sure I do that in the right way. I have to repeat the mu n times. Otherwise, my location, let's say 1, 3, will be repeated column-wise, 1, 3, 1, 3. And suddenly, each other sample comes from a different location. I will not get an elliptical distribution. Be extremely careful here. Good, so I can do that. And then I get, you see the normal, the black points, and then overlay the t. And of course, the beauty is that my w is not bounded. Yeah? So I reach out much further than any other normal distribution. But of course, I can play now. I can say, okay, I want to have a multivariate t. Here, an independent one, the black dots. You see almost a cross here. Yeah? You almost see no points in these corners. There's no dependence. But then I want to have an uncorrelated t. Remember, for the normal, independence equal to uncorrelatedness. For the t not, because you have the square root of w there. The only normal variance mixtures where independence is equivalent to uncorrelatedness are the ones where your square root of w is a constant, and those are only the normals. Yeah? So you see more points here. You see the spherical shape, so that's actually a spherical, if you like. And then the full T, which introduces the red points, which introduces dependence in 2 ways. First through the square root of w, and then through the correlation matrix. Yeah, so this is how these samples differ. But let's now quickly, in 1 minute, let the fun begin. So I would like to look at a square root of w where the w only takes on 2 values. So I kind of see a little bit more what's going on. So let's do that. And then what you see is, so the black dots are my multivariate t. And then here you see samples from a normal again, but here the w is 1, and here the normal with w being 2. And with probability 1/2, they are 1 or 2. So you see half of the samples in the blue cloud and half in the red cloud. And you really see how the t is now constructed. Essentially, you overlay normals with different realizations of your w. So you overlay normals with different covariances. But if you only use 2 different values or any other distribution for your w, which is bounded, essentially, then that bound is essentially the max correlation you get. You will not reach out further. But the beauty for the t is, of course, that the distribution of the w is unbounded. So you do reach out much further every once in a while. Yeah? So this is kind of the beauty behind this. And then I can also look at a mean variance mixture. This is now what I mentioned before. I can also mix the mean. So half of the sample points have a different location, essentially. And then you see overall they are not elliptical anymore. Yeah? But play around, adjust the probabilities to do all of that. So it's all there to play around. Good, and then I can look at the ellipticals. So I start from the spherical, as you've seen on the slides before. I can now first add the Cholesky factor. Before I first added the radial part, essentially. Now I first add the Cholesky factor to see what it does to my circle. And it tilts it, so you already see the elliptical shape. And now my radial part essentially generates as many points as here and scales out each of them with the corresponding realization. And then you will see the elliptical shape overall. So if I now add, and add really means here should really mean multiplication. So if I multiply with R, then each point gets scaled out in a different way, or possibly scaled in, right? So, and then of course I can also add a location and move the whole sample cloud. And also I can look at two point distribution for the radial part, and you really see that, well, you have the circle before, and if I only have two radial parts, two realizations of the radial part is two different realizations, then you see that I only get these ellipses, right? So as before with the nested circles, essentially. Yeah, so again, an elliptical distribution just overlays these ellipses for different radial parts. Yeah? And of course, if the radial part is unbounded, then you get further and further out. Yeah? So yeah, that's essentially it. Enjoy your lunch.
Okay, so I think we will slowly make a start. Okay, so in the first session after lunch, you're going to get 45 minutes of me talking about dimension reduction, and then we're going to change the subject and start to talk about copulars and dependence. That will be Rüdiger. This morning in the multivariate modeling chapter, we talked about models for random vectors of dimension D. We talked about normal mixture models, variance mixtures, mean variance mixtures, and also a little bit about spherical and elliptical models. One comment I will just make is that these mixture distributions are remarkably easy to estimate. And some of the material we have in QRM tutorial for Chapter 6, you'll see that there's about 7 or 8 scripts for Chapter 6. One of them is about fitting multivariate mixture models, whether student distributions or generalized hyperbolic distributions. It's very easy because of their structure. They are scale and location mixtures of multivariate normal, and in a sense, they make use of the convenient estimation of the multivariate normal and are not too much more difficult to estimate themselves using algorithms which belong to a set of methods known as EM algorithms. Okay, I will talk about factor models. The dimension D of our random vector may be extremely large. If we're thinking about all the risk factors that affect a portfolio, D could run into the, I don't know, thousands or tens of thousands. Even if we restrict to something like portfolios of bonds, we may have a high dimensional situation because we have so many different times to maturity. The reason we're doing this section is that we will use it in 2 applications on the remaining 3 days. Tomorrow morning, we will use dimension reduction on bond portfolios, and on Friday morning, we will use dimension reduction in portfolio credit risk models. So the factor models, it will be presented today as a tool, and then it will be used in 2 applications. So the idea is to, let's see. Okay, so our random vectors have been called X, our vectors of risk factors. The the p-factor model is an attempt to explain the randomness in a d-dimensional vector in terms of the randomness in a lower dimensional vector of factors. So F stands for factors. We may want to go from tens of thousands down to dozens, potentially. So from tens of thousands down to dozens, possibly even down to one, possibly even down to a single factor in certain applications. So the factor model for a random vector looks like this. It could be called the linear factor model. So you have various elements. B is called the loading matrix or the weight matrix. This is going to have D rows and P columns. So as many rows as there are risk factors, and as many columns as there are common factors. At this point, it becomes confusing to talk about risk factors and factors, but so we'll call, this is the variable x, and these are the factors, f. The dimension of fp, when we need it, we will call the covariance matrix of f, we'll call it omega. In general, they might not be independent or orthogonal factors, but they can usually be orthogonalized. I'll come to that. Epsilon are the errors in the factor model. They're sometimes called the specific terms or the idiosyncratic terms, and they're supposed to be uncorrelated with each other. So this vector of idiosyncratic error terms will assume it has mean 0, and whatever covariance matrix it has, in the factor model, it should be a diagonal covariance matrix. So sometimes when we encounter it, it may be called, this is upsilon, one of the lesser used of the Greek letters, so that one's upsilon. The factors and the errors should also be uncorrelated. The factors, this part is sometimes called the systematic part. So we want to use this kind of model to reduce dimension. And I'll mention 3 strategies for doing it, and I will implement at least one, and if I talk fast enough, possibly 2 strategies for doing the factor modeling. If we assume this structure for the random vector, it's actually the same as assuming a structure for the covariance matrix of X, as you will see. So perhaps go to the second point first. I mean, the factor model implies that the covariance matrix of X has this special structure. You have the loading matrix or the weight matrix, you have the covariance matrix of the factors, B again, and then this diagonal covariance matrix of the specific errors. You can, as I've said, you can orthogonalize the factors. You can define an F star in this way, and you can define a B star, a matrix in this way, and you can rewrite the model in terms of B star and F star. So I've gone here from B and F to B star and F star. The point here is that the covariance matrix of F star is now the identity. So the covariance matrix of X will be given by B star transpose plus upsilon. So you can always orthogonalize the factors once you have them. Now, the question is, where are we going to get factors? So our goal will be to identify factors Ft, and then we will, instead of modeling all of our individual prices and rates, all of our individual X information, we will concentrate on modeling F. That's going to be the point. Okay, so the various strategies. So to estimate a factor model, we need data. We will assume that at various time points, we have X data. So we will have a data set of size n. We will have n d-dimensional vectors xt. And we assume that at every time point, the factor model holds. It's customary to divide the strategies into 3 groups. The names, you see different names for these, and I'll mention some of them. 2 and 3 should have a different name. I think this is one of the first typos we've actually come across. This fundamental should actually read statistical. So if you take a pen, cross out the 3rd fundamental and write statistical. So beginning at the top, econometricians refer to something called macroeconomic factor models, also known as time series factor models. This is a situation where you have some observable candidate for the factor. So you might decide, for example, so in modeling stock returns, you might take a stock index as the factor, or you might take sector indices as the factors. So you probably know these models in econometrics or in economics. CAPM is a model of this kind, a macroeconomic factor model, where typically you take the factors as observed index return series or sector index return series. And if you observe FT, then the problem of calibrating this model, or should I say estimating this model, it will be estimation, is to determine A and B. And this is a regression problem. This becomes a time series regression problem. Given XT, given FT, determine A and B. Now this, I won't do more, there is in the QRM tutorial, there's an example of each of these kinds of factor models. The one that I wasn't going to do was this one, but I was going to do fundamental factor models. So this is a slightly different situation. And here, what we assume is that we observe B. Okay, we don't observe F, T, we observe B. We assume that the matrix of factor loadings is known. And we attempt to estimate the factors. The factors are unobserved, so we attempt to estimate those. Again, it's a regression problem, but instead of being a longitudinal time series regression problem, it becomes a cross-sectional regression problem. So these models that are quite popular in fund management, where you look at the fundamentals of stocks, such as the country, the industry sector, and the size, large cap, mid cap, and small cap. So people working in fund management sometimes call those fundamental factor models, because these are the fundamentals of the stock, industry, country, size. So that would be an example. So basically we can classify each of the individual X's into groups which are associated with things like industry or country. But we don't have a factor for that group. Perhaps we don't have a natural candidate for the factor for that group, so we will actually estimate the factor for that group. We will construct it. So at every time point, we will run a cross-sectional regression. And I'm going to do this so that you see how it works. The statistical factor models, nothing here is observed. In the statistical factor models, we have neither the factors nor the factor loadings, so we have to get both. Somehow we have to discover the factors within the X. So that, for me, it's quite a nice division. Here you observe F, but not B. Here you observe B, but not F. And here you observe neither. Okay. So I will miss out the first kind. I will miss out the macroeconomic factor models and go immediately to the fundamental factor models, and then we'll try and do that. So at every time point, we have a model of this kind, and the bit that's... Okay, now we're live again, I think. So B is known. It's some classifying matrix for every one of these X variables. And let's just take the example of stocks. So we'll call the X's now stock returns, and we know the classifying matrix B. So we have to observe FT. We have to estimate FT. We can get rid of A. So going back to the more general model, we can actually absorb A into FT. So the problem will be estimating FT. It's a regression problem, so you probably recognize something which looks like and which is a least squares estimate here. So the first thing we could do is we could try and estimate at every time point t, we could form the ordinary least squares estimate. So this is the sort of matrix form of the ordinary least squares estimate. If each of these error vectors, or the components of these error vectors, if they all had the same variances, that's what homoscedastic means. If they all had the same variances, this would be the best unbiased estimator. But in general, it's not possible to observe that because these are different stocks at time t. Some of them may be more variable than others. And so to get slightly better estimates, you use weighted or generalized least squares. But that's a detail, really. I think the important thing to take away is you use standard regression. You start with ordinary least squares, and then you try and improve it with generalized least squares. And I'm going to do an example of that, or attempt to. So fitting a fundamental factor model. This has been resized since yesterday. Is the font okay at the back, or should I make it one bigger? One bigger. That's maybe better, right? It's a little bit better. Okay, so for this, I will need the time series library. I'll use QRM data again. I'll use the data that Marius and I have put together and the QRM tools library. I'm going to take every single stock in the S&P 500. There are, how many stocks are there in the S&P 500? It appears there are actually 502 when we have a look at them. I'll take the data from 1995 up to the end of 2015. So 502, there are 505 in the S&P 500. So I have 5,200 days, and I have 500 stocks. And I will do a monthly model. So I'll go from daily to monthly, and I will fit basically a cross-sectional regression every month. There are a lot of missing values, and so unfortunately I can't take all 505. Some of the stocks have an awful lot of missing values. Let's see if we get a picture here appearing. Yeah, this is actually just the first 100 out of the 500. If you see a black bar, this is time. And if you see a black bar, those are missing values. So for example, this one we only have data from here. These ones we have the complete data. This one we only have data from here. So there are missing values. I'm going to get rid of every stock where I have more than 10% missing values. Let's see, or omit columns with more than 10% missing values. And I will then fill in other missing values. So I'll use a function which is in the XTS package called NaFill, which will interpolate to get rid of other missing values. And by the time that finishes running, I've got 374. So unfortunately, a lot of these S&P stocks are relatively recent. They don't go back all the way. I won't draw all the plots. If you want to see 374 time series, you can cycle through this block here, and then you will see 20 by 20, you'll see 374 time series for the Standard & Poor's. I won't do that, and I will throw out a few other things. So I'm going to remove certain stocks. The ones which essentially collapsed, but which appear to be still there in the data set, like AIG, I'll throw them out because they essentially go to 0. I'm removing the telecoms because this is a very thin sector. The kind of fundamental factor model I will fit will be based on industry sector. And telecoms is the thinnest sector. There are only 4, so I've thrown them out. Not absolutely necessary. And then there are a couple of names which basically are moved together. So there's a CMSA and there's CMCSA and CMCSK. They essentially move together. So I throw those out. So certain are ignored, just a few, but I don't think that that's important for the purposes of understanding what's going on. But by the time that I've done that, I'm down to 365. So D is 365. The dimension of my vectors is 365. I will take log returns, as usual, we'll just build the log returns. We'll plot them shortly. First, I will turn the daily log returns into monthly. So I'll take monthly data, and I'll plot the first 20. Okay, so that's now the first 20. of these stocks here. You may see certain tickers that you recognize, but yes, these are monthly log returns for the first 20 out of 365. Now, I need sector information. I need to be able to allocate every one of these to a sector, and this is the breakdown by sector. I have major sectors and subsectors. So the major sectors are things like consumer discretionary, financials, industrials, healthcare, as you can see. And the subsectors I won't worry about. I will use primary sector as my classifying piece of information. I'll just go through a few commands that are not important, and I will do the tabulation. So of those 365 stocks, 57 are consumer discretionary, 31 are consumer staples, and so on. 25 are utilities, 63 are financials. I'll shorten the names. Some of those names are quite long, so I'll shorten the names. And then finally, in step 2 here, I will fit the model. So I want to fit a cross-sectional regression model every month. And there's no intercept. All that I'm estimating is the factor values for these 9 sectors every month. And I can do it in R. Regression is so easy in R. You use a command called LM. You don't need a loop. You can accomplish everything by putting matrices in each of these positions here. So when I execute this command here, I've completely calibrated the factor model. And we can have a look at the information that I essentially use. B is the loading matrix. B is the loading matrix. There are 365 rows, 1 for every firm, and there are 9 columns, 1 for every sector. So when you look at this, what it is basically a matrix of zeros and ones. So let us take, have a look at the first title, triple M. The primary sector of triple M is here industrial. That's an industrial. The primary sector of ABT is health. Okay. So every one of them is uniquely attributed to a sector. A sort of classic fundamental factor model. Of course, these models are so widely used in the asset management industry. You have the Barra factor models are of this fundamental type, for example. What do these factors look like? So every day I've estimated a factor value, and I can now plot the time series of factors. So this is my constructed factor for consumer discretionary. This is my constructed factor consumer staples, IT, utilities, etc. So I build these factors, and what I can do now is I can say I've gone from dimension 365 down to dimension 9. I will concentrate on modeling these 9 factors in future. And everything else, hopefully, all the noise, all the idiosyncratic errors are second-order effects that diversify away and are less important from a risk point of view. That's the idea. The residuals. I can estimate residuals. Going back to the factor model, having estimated FT, I can then estimate epsilon t. Those are the residuals. As I've said, the variances are unlikely to be equal. So it's not going to be a situation of homoscedastic errors. And so usually what one does then is one does a weighted least squares. The weighted least squares estimator is given here. Okay, you have to basically estimate the covariance matrix of the errors, upsilon, and actually there should be a hat here. This should be upsilon hat rather than upsilon in what you actually compute, but that's a small detail. So this EPS variances, I've basically just computed my estimate of the covariance matrix of the errors, And you can have a look. I will sort them from smallest to largest. So there's the 365 names. And these are the variances of the errors, starting with the smallest variance, D, and going up to the largest variance, whatever it was, REGN. So in a sense, the first titles are the ones which are best explained by the industry factors, and the latter titles are the ones which are least well explained by their industry factors. I think we could interpret it that way. Generalized least squares, model 2 here, the generalized least squares, you just add weights. And I can re-estimate my factors. They won't look a lot different. I will do that, and if you watch the pictures on the right-hand side, I just changed the pictures. It hardly changed. You maybe saw a little bit of movement, but those are weighted least squares estimates. The factors are correlated. Here's the correlation matrix of the factors here. So some of them are more heavily correlated than others, but you can see the matrix of correlations of these factors that I have constructed. And it's probably nearly enough. The errors should have a near diagonal correlation matrix. So when EPS stands for epsilon, so I'm trying to reconstruct epsilon, the errors. So I extract the residuals, I call them epsilon. You'll often see T's, and you have to sort of keep your wits about you in taking transposes and not taking transposes, but when you do it, you work it out. So don't worry about these T's. Certain things are transposed, other things aren't transposed, but all the linear algebra works out. The residuals should have a correlation matrix which is near diagonal, because that's the assumption of the factor model. The factor model says that these errors should be uncorrelated, so therefore their correlation matrix should be diagonal. And in practice, if it's a great factor model that I've fitted, my estimated correlation matrix should be near diagonal. So I think that's the last thing I'll do in this example. I will estimate the correlation matrix, and this correlation matrix is 365 by 365. Rather than attempt to show you a 365 by 365 correlation matrix, I will have a look at the upper corner. So the upper corner, I've basically taken the first 75 stocks, and so this is the upper 75 by 75 corner, and this is a picture of a correlation matrix, a level plot. And you see the scale here. If it's white, the number is at 0. If it's red, the number is going up towards a half. And if it's blue, it's going down towards, well, it's going up towards 1, and it's going down towards -1. But this already tells you the range of these numbers. Evidently, there isn't an estimated correlation bigger or much bigger than a half, or much smaller than -0.3. So if you... You see what I did there? I just put NAs on the diagonal, because if I put, what you get is you'd get a really harsh purple line on the diagonal. We don't want to look at that. We don't care about the diagonal, so I put some NAs in there.
As long as it's 1, it's okay.
Yeah, okay. Yeah, don't worry. It really is 1, but I put some NAs there. And so what you look for are the darker squares. If it's darker pink, let's take that one, that's sort of badly modeled by the factor model in the sense that the error is large and positive. And if it's darker blue, take that one there, that's badly modeled by the factor model in the sense that it's large and negative. But I like to think that this is a fairly pale picture, and in other words, that it's not a bad factor model.
Would it happen that, you assign every firm only to one industry, some are active in various sectors?
Yeah, so it's a simple so every firm in the S&P is officially categorized in one main sector, and then within that main sector into a subsector. So there is no data on multiple sector membership here. And clearly, I suppose some companies are easier to attribute than other companies. Not being an asset manager I'm not really an expert on this, but every company is uniquely identified to one main sector. And so you can obviously imagine that certain companies are poorly explained by their sector factor, and other companies are very typical of their sector factor. And this picture gives you some information. We could do the 365 by 365, but it just starts to look like some kind of abstract art. The errors should also, so I won't continue with this script, but there are a few more things that are investigated. The errors should also be uncorrelated with the factors, and there's other things you can look at. But I just wanted to give the key idea. A fundamental factor model, you attribute the stocks or the individual risks to certain classifying variables. Sector and industry, I would have liked to have, country and sector. I would have liked to have done country here, but they're all American effectively. So we could have thrown in some worldwide stocks and done country industry factor models. They're in the S&P 500, so they're all large in size, so we can't do the large cap, mid cap, small cap. It would have been nice to have more than one factor going on here, but I've done basically just industry as a factor. So hopefully you see how that works. We use that factor modeling philosophy tomorrow with interest rates, and we will also use another factor modeling philosophy, which is probably more familiar to people, and that is the PCA philosophy. So really quickly, I will show the PCA philosophy. This is a statistical factor model, so we know we don't know what the factors are, we don't know what the weights on these factors are. Yeah.
I could go back one slide, sorry to interrupt you.
Yeah.
So given you have now fitted your FT, I suppose you will also do something on top of that in order to forecast, say, so you have the...
Oh yeah, so...
I guess the next part of the story is that you specify some model for your fitted...
Factors.
For your fitted factors, yeah.
Yeah, the next part of the story is the factors become now of primary interest, and the whole task becomes to forecast the factors, because most of the risk is in the factors. The stocks are well explained by the factors. They have their own idiosyncratic risks, but if I am invested across the market, those diversify away to some extent, but I can't avoid the risk that's in these industry factors, or more generally in the broader market. Yeah, so I reduced dimension from D to P, from 365 to 9, and then we could fit 9-dimensional distributions, or indeed 9-dimensional time series models. Could do a 9-dimensional gauge, and that's my ambition this afternoon, depending on how things go, to do something like that, 9-dimensional gauge. The PCA, the theory of the PCA is, if you're seeing it for the first time, you need a bit of time to digest it. If you've seen it before, you probably don't need to look at it, and I want to wrap this up in 10 minutes. So really I wanted to do PCA without telling you too much about how it works. We have to both find the factors and find the loadings. Find the factors and find the loadings. And what we do is we apply a decomposition to the sample covariance matrix, a spectral decomposition to the sample covariance matrix. It works for any symmetric matrix. Any symmetric matrix admits a decomposition of this kind in terms of an eigenvalue matrix and an eigenvector matrix, and we apply that to the sample covariance matrix, basically. So we apply it to a covariance matrix, we decompose into eigenvalues and eigenvectors, and we make a transformation of the original data. The transformation looks like this. We take the matrix of eigenvectors and we transform the x data, and that gives us y. That doesn't reduce the dimension, because I just go from d-dimensional vectors to new d-dimensional vectors. So I don't reduce the dimension, but what I do get are vectors which are then orthogonal. This is the principal components transform. The components are then uncorrelated. And usually the way that I form this matrix is in such a way that the eigenvalues are ranked from largest to smallest, and the eigenvectors are arranged accordingly. And I take the first few principal components, 1 or 2 or 3. I take the first few components of the y vector as my factors. So missing this out, what I do is, I think we just go to this. How is it a factor model? I make the principal components transform. I find the eigenvectors of the covariance matrix. I take the first few, because I've arranged them according to eigenvalues from largest to smallest. And the idea is that the first few linear combinations are the ones which explain most of the variance of x. So most of the variance of this vector x can be explained by the first few principal components. So I basically use the first few components of y as my factors. So I will call y1. So y1 contains the first k components. Those will be my factors. And y2 contains the remaining components. Those essentially will be the errors. Now, this will never give a perfect factor model, because there's nothing in here which says that these error vectors are uncorrelated. But it's a very commonly used strategy. And I'm just going to do it because you'll learn something by seeing this carried out. I won't do it with exactly the same data. So this is PCA factor models. I won't do it with exactly the same data, just for I'll actually just do it with the Dow Jones data. That's a smaller dimensional world, a 30-dimensional world. So I need the same libraries. This time I'm going to take the Dow Jones index. So I go to dimension 30 effectively, although I will throw out a couple. That's the Dow Jones Industrial Average. Of the 30 stocks in this average, certain of them are missing. This is the picture of missing values. So I'll throw out these two. There are a few missing values with these ones. I can't remember what the names are, but I throw out 2 of 30. So there are now 28. And we can plot what we've got. It should appear here. So this is now my data. So it's only 30 this time. So it's a little bit easier to see what's happening. And this time, the first one is Apple up here. So remember that Apple is the first one. I need the log returns. That's the returns on the index itself, but this here is these here are the returns for the stocks. And again, I'll just use monthly data. So I will use monthly data once more. Okay, so that's going to be the data that I apply a factor model to, but my factor model, it will be done by principal components. And so this is the command here that does it. Determine the principal components. In fact, there's 2 functions that do the same thing. I'll use the first one, princomp. And so I will do a principal components analysis, and then we'll look and see what that gives us. Okay, so I've carried it out. The summary, well, the numeric summary is not all that interesting, but I'll show you 2 things now which are probably useful. So being a 28-dimensional vector, there are 28 stocks. There are 28 principal components that can be looked at. And these are the variances of the principal components ranked from largest to smallest. So you have a situation here where this bar represents the variance of the first principal component. This is the variance of the second. This is the variance of the third. And I have to decide where I'm going to stop. I'm going to reduce dimension from 28 to something a lot smaller, maybe 1. Maybe I just take the first principal component. Maybe 2, maybe 3. But I'm going to say that these principal components capture the most important features of the data. But what are they?
So the principal components are a linear combination of your stocks.
Yes, the principal components, and this is what will show you that. Have a look at this. This is what they are. Component 1. So component 1 is a linear combination. These are the elements of the linear combination. It's minus 0.28 Apple and minus 0.25 American Express. So that's just a vector. Component 2 is plus 66% Apple and minus 16, well, it's not a percentage, but it's 0.66 Apple, minus 0.16 American Express. This means the number is very small. It doesn't mean it's really 0, but the way that the loadings are plotted in the PCA analysis, if you don't see anything, it means it's smaller, I think, than 0.1. So immediately your eye is drawn to the larger loadings, whether negative or positive. Now, the first component, all of the signs will be the same because it functions like an index. It is simply like an index, although the weights are not all equal. You can see these weights are not all equal, they differ, but it functions like a kind of, this linear combination represents like a market index.
Is that always like that?
Yeah, with stock data, yes. With stock data, it will look like that.
What's so special with stock data that would happen?
I guess it's CAPM. They're all to some extent following the broader market. It's difficult to have a stock that, I mean, you have ones which are sort of counter-cyclical, which buck the trend, but to some extent they all follow the broader market.
Oh, because they're all kind of in sync. We both saw that 2009 and 2001 were...
Yeah.
Okay.
Well, weight is by market capitalization. Money flows from one company to the other in trading. So if new money flows in with the right weighting, the average of the returns should always be the same. There must be a linear combination that is constant because you sell one stock and someone else takes it. I think you can find a random boundary condition like that.
Of course, this isn't the complete market here. These are all, big titles. This isn't the complete market, and
It's not market average weight.
it's not.
Dow Jones is price weight.
It's price weighted. So if you just have a look down, every sign is negative.
The first column, almost all values are the same, so there is no interpretation.
They're quite close, certainly. They're not all the. They're quite close, but. So this is the linear combination that actually maximizes the variance among all possible linear combinations. I missed out the interpretations of these things, I sort of missed out. The first principal component is the standardized linear combination of X, which has maximal variance among all such combinations. And then from then on, the jth is the standardized combination, which has maximal variance among all linear combinations which are orthogonal to the ones before. So that's what they are. And yeah, so these are these are simply the eigenvectors of the covariance matrix. That's what they are. They are the eigenvectors of the covariance matrix. Let's just use the first 3 to define factors. I'll take 3. I don't know why I took 3. I could take 2, but in this script here, I take 3. The factors are called the PCA scores, or the complete set of them. The estimated principal components are called the PCA scores, and I will take the first 3 and plot them. So that's, if you like, the first 3 principal components. Component 1, component 2, component 3. That's how they behave. Stochastic volatility, I'd say, in some of these. Again, it's based on monthly data. These are orthogonal by design. So if I now look at the covariance matrix of these three, that's the identity. These are 0, effectively, so that's the identity matrix. They are...
That's interesting. 2009 is kind of, in 2001, somewhat disappeared.
What are you saying, Frank?
Well, 2009, before, when you looked at the individual stocks, you saw something very peculiar in 2009 and around 2001 also. Here, I mean, 2009 is really quite different from what we had before.
2009 is here. Well, let me do something. Let's take that first principal component, interpreting the first principal component. First principal component. I will show you the first principal component. That's the returns on the Dow Jones Industrial Average, and that is the movements of the first principal component. What do you see here? It's a little bit like as if this were a mirror, a little bit like they're flipped over. So let's change the sign of that and plot that against that. And so this is the Dow Jones Index returns plotted against the negative of the first principal component. So you can see they are, highly correlated, but they're different. So if you like, the first principal component is an alternative index, so returns on an alternative index weighted according to the mathematics of principal components. So that's very brief, but it's just another way of getting factors out of the data. What is better, fundamental factor models or principal components? They both work quite well, it appears, and both have their advocates, and companies have built their businesses around fundamental factor models in particular. Principal components always works remarkably well in extracting linear combinations, linear, if you like, linear weighted portfolios, which carry a lot of information. If the first component acts like an index, what is the second component? If the first component is like an index, what is the second component? Just have a look at the weightings, the loadings here. Okay. Have a look at the second one. Okay. Apple, 0.663. Negative, negative, negative. Cisco, 0.215. Small, negative. What else do we have? IBM, 0.128. Intel, 0.357. Johnson & Johnson, negative. Coca-Cola, negative. Microsoft, positive. It's like a contrast between anything to do with technology and everything else. Okay, so the first one comes out like a contrast between technology. The second one is like a contrast between technology and everything else. Having said that, if I use this as a factor model, and I'll just cut to the end now, basically, and show you another of these pictures. If I go to the end now, so I take these as factors. I then look at how good is the factor model. I look at the errors, and I make the same kind of picture of the correlations of the errors, as if I use the first three principal components as the factors. Again, a lot of white in this picture, but bits of dark red and bits of dark blue. The first row and the first column is Apple. Apple is the one where the colors are darkest, I think. So Apple is like, even in this model, Apple has dark blue and dark red squares, and so is a kind of law unto itself, you might say, as far as its returns are concerned. But, okay, the important thing is not analyzing stock returns, which obviously I don't do professionally, but different techniques for getting factors. That's what you're to take away. Any questions? Yeah.
It's not the biggest problem with the principal component analysis that those factors do not really make economically sense.
Yeah. So the principal components, it's a very good point. People usually say, well, these are factors that you discover by mathematics or statistics, and a priori, they may not make any sense. When you do it with stock returns, they do make a kind of sense. As I've said, the first one is like a market portfolio. And the second one is always some kind of contrast, but then the third and the fourth and the fifth, what are they? Sort of higher order kinds of contrast. With the stocks, you get some sort of interpretation, but if I took all of my financial risk factors, if I threw in my exchange rates and my volatilities and everything and just did a PCA, something would come out, but it might not make any kind of sense. Whereas the other two kinds of factor modeling, some thought goes into either what should be the factors or what should be the factors? Either you identify particular time series to act as factors, or you classify your data into groups and manufacture the factors.
In your experience, how robust are these principal components? Suppose you do the same exercise now in 2 years from now. Are they going to look completely different?
I doubt they'd look completely different. The first two will still, I've done this thing over and over again with the stocks. The first two always come out much the same way. Probably we should do it on the broader market as well and see what comes out. But yes, it's based on the covariance matrix, which if you badly estimate a covariance matrix, obviously you're going to badly estimate the principal components. And with heavy-tailed data, the problem of estimating a covariance matrix is quite a serious one as well. So, yeah, there is a robustness issue in what comes out.
So when you think heavy-tailed are important to destroy the robustness, so after a crisis, you might have a big change in your principal components.
Could do, yeah. I haven't analyzed this to destruction, but in so much as it's all based on the covariance matrix, and covariance matrices, standard estimators, if you use standard covariance matrix estimators with heavy-tailed data, they're not very robust, then that must have some repercussions in what comes out. We wanted to mix it up a bit this afternoon, and we have a big topic coming up on Thursday morning, which is copulas and dependence. And we thought that if we hit you with a ton of copulas and dependence on Thursday morning, it might be overload. So we wanted, while you're fresh, we wanted to ease you into it, which is why we thought we'd just do a little bit of factor models and now do a little bit of copulas and dependence, which Rüdiger will do. This before the coffee break and a bit after the coffee break. And so for those who got completely lost with PCA and factor models, you can reboot, and you're now going to hear a little bit about copulas and dependence.